seminar from the University of Washington. Before I introduce today's speaker, I want to take a moment and acknowledge that the University of Washington does sit on the traditional lands of the Duwamish people, most of whom are now members of the Muckleshoot Nation. Today, it's my great pleasure to introduce Professor Daniel Apai from the University of Arizona. Daniel, as probably many of you know, is the leader of one of the large NExSS teams, the Alien Earths group based out of the University of Arizona. It's a sister collaboration to the University of Washington's virtual planetary lab. In addition to leading that group, Daniel is also a member of the lead council for the NExSS group run out of NASA. That's the NASA NExSS for Exoplanet and Solar System Science. He's also had a long career looking into brown dwarf atmospheres, stars and planets, astrobiology, a lot of things. I can't cover all of them at this time. He's also recently put forward a fascinating new idea for a space telescope to potentially image exoplanets. Today, Professor Apai is going to be giving us an overview of the Alien Earth group. So we get to hear all about the great things that they are up to. As usual, when we meet virtually, I'm going to ask all of you to please mute your microphones and turn off your videos so that Daniel has all the bandwidth he needs. I'm also going to ask that you please hold your questions until the end. If possible, I would encourage you to please turn on your camera and ask your question directly to Daniel when you have the chance. Of course, if that's not an option for you, that's fine. You can leave your video off, or you can also type your question into the chat, and either I'll read them off or you can read them yourself later on. So with that, I think I'm going to do what I suggested and turn off my video and sound and pass the baton over to Daniel. Please take it away, sir.
Thank you very much, Rory, and thank you all for joining. I appreciate this is a Thanksgiving week, so I know many of you may have been taking time off and traveling, and I appreciate for you joining the talk today. And thank you for the invitation too. I'm unfortunately couldn't come in person, but I enjoyed meeting many of you via Zoom. And I'm happy to tell you more about the project after this talk, or if you have other questions later, just feel free to contact me. So as Rory mentioned, the talk here today will cover and provide an introduction to our project Alien Earth. And also I included plenty of science results that all tie together in a framework that I will describe that I think is I'm particularly excited about. These all relate to how we search for habitable worlds around nearby stars. And that search, I do mean beyond actual observations. I mean the framework for carrying out that search, interpreting the results, guiding the follow-up observations. So the work that I will describe is not done by myself alone, but it is in almost all cases a result of a larger team. So I will try to highlight the first authors and lead authors of those studies. I wanted to start this talk by basically this bit of a strange dual subtitle, Life Beyond the Solar System and Life After Astro 2020. And for those in the community, you probably all understand this. We have spent years waiting for this Astro 2020 report that came out about 2.5 weeks ago, and it is providing now much clarity for our field how to proceed. And it also, I think it's a very interesting intellectual framework to kind of explore what we will do next and what questions we should be all focusing on. But to understand really the recommendations of the Astro 2020 and how that relates to, in particular, our research, I wanted to start with this animation here. And this is basically an animation that shows the number of known exoplanets and exoplanet candidates once I started. On the x-axis, you see the year. And what I want to point out is that we all know that we live in an exciting era of exoplanet exploration where the numbers are growing rapidly. We find more and more planets. So let's see how this played out. So really the first discovery started in 1995. People figure out how to use radio velocity to find more and more planets more and more efficiently. We start to have transit surveys delivering more and more planets. Kepler kicks in, provides even more planets. And you see an exponential growth here, basically. What is even more exciting is what's coming. So we have seen this exponential growth, and that is actually set to continue. So I provided here the TESS yield, the Gaia yield, the Plato yield that is expected, and I didn't even include the Roman Space Telescope's yield, which may be many tens, maybe even 100,000. So there's an enormous increase that still has to come. The vast majority of planets we still have to find, and we'll find them. These missions are in the pipeline. So we have already vast information and access to information on the exoplanet population that is extremely valuable. At the same time, our understanding of individual planets hasn't grown that much. So our ability to find planets is now benefiting from Moore's law, and we can do many of these searches parallel, for example, transits and microlensing, but characterizing the atmospheres of planets, detailed studies of individual worlds, that is something that still requires very significant resources and is done on a one-by-one basis. So actually the number of planets that we can characterize in great details remains basically maybe a dozen or so each year. It has not been growing that much. But exactly that kind of observation is what we need in our next step or search, where we want to explore potentially habitable planets and identify those that may carry atmospheric compositions or signatures that we could attribute to a potential for hosting life. So I think most of you are familiar with the methods I'm going to use in the rest of the talk, but I just wanted to provide a very brief introduction just for the key concepts here. So when I'm speaking about searching for life, broadly speaking, what I really will mean in this talk is searching for atmospheric signatures of that may be indicative of life biosphere existing on a planet, and I will address this in a little bit more detail. Well, how can we do it observationally? We basically have to provide some sort of an analysis of the atmospheric composition, what gases make up the atmosphere, and identify those gases that may indicate or may even require an active biology to be present. So the way to do this, there are different ways, but fundamentally we need basically to use starlight as a light source, and observe maybe light that filters through a planetary atmosphere, or planet that is reflected or scattered back in the lower, as shown in the lower panel, from the planetary atmosphere and surface. In both cases, the starlight and its energy as a function of wavelengths is modified by the presence of absorbers, molecules that will be able to interact with the light of certain energy, absorb it, re-emit it, or scatter it. And if we can get that spectral information from methods like these, then we may be able to identify what the atmosphere is made of. So in the lower panel, I show a really nice figure from in this case from the LUAR team, which is one of the major mission concepts put forward to the decadal survey, with very significant input here from the University of Washington VPL team in making this figure. And this basically spectrum on the right-hand side is from a simulated data set in which a solar system would be observed in a way with a very large telescope, that the star and its light would be suppressed in the center. So these are examples, and I will speak a little bit more about these techniques, but let's first stop for a moment just to consider what is that we can detect and what is that we could not detect. So it is tempting to think that we are searching for advanced life forms, but that is not the case. We don't really have good abilities to detect advanced life, except maybe for technosignatures, which is exciting but not covered in this talk. What we may be able to find, however, are global ecosystems, basically ecosystems that succeeded in controlling their environment to the level that they changed it. So our best and currently only example for this is Earth, where we have seen as a function of time, as shown in the lower right in this nice figure from Jada Arney and collaborators, that shows the composition of Earth's atmosphere starting from 4 billion years ago to the top of the panel, going all the way down to 0, which is present day. And it shows basically a sketch of how the atmosphere has changed, with Earth starting initially in a carbon-rich, probably methane-rich atmosphere, where hazes may have been very common, and then going through the Proterozoic Earth with trace amounts of oxygen. Nevertheless, the redox state of the atmosphere and the planet has changed to modern day, where the oxygen is a major part of the atmosphere. These changes basically represent oxygenic photosynthesis, establishing a foothold and then dominating the planetary atmosphere in terms of sources, outweighing sinks, and filling up the atmosphere with oxygen. This is a kind of change that we may be able to detect even through interstellar distances. Oxygen 2, the molecular oxygen or ozone are examples on Earth, for example, that are direct consequences of oxygenic photosynthesis. This, what kind of biosignatures we may look for, how to interpret them, has been discussed, I'm sure, on this seminar series too, and it's a fascinating topic. But today I will take a little bit of a different approach here, but I wanted to point out some of the relevant works. Of course, there are many more. So the Astro 2020 was basically a process that was pretty much culminating 7 years of work by the community, providing a consensus on our next steps in exploring habitable worlds and then building missions that can search for signatures of life. I think, and this came out, so we are all excited about this. I think many of you probably have read parts of it or all of it. It is a 700-page long document, so I will just touch on a couple of the key points that I thought were very interesting for this particular talk and this particular community. So first of all, the search for habitable exoplanets and atmospheric biosignatures is really central to the Astro 2020 recommendations. It really came, you can see even in the cover page how well exoplanets are represented. It is at the forefront of the report, and it drives many of the recommendations. The Astro 2020 did recommend a US ELT program, which I'm very excited about, Arizona being part of the GMT, and also from a scientific standpoint, an amazing facility. It also recommended reviving a probe class mission line, which I think is also an excellent idea. So this would be $1 billion intermediate size missions compared to a flagship. But perhaps most importantly, it recommended a 6-meter mirror diameter telescope with an approximate cost of $11 billion and precursor technology maturation. The goal of this mission is to study about 25 habitable zone planets, and that assumes a certain occurrence rate, eta Earth, for Earth-sized planets in the habitable zone. And I translated this. I mean, I think this is an interesting number to keep in mind, that this translates, taking this best case scenario of 25 planets, to about $500 million to $2 billion per planet. So that already tells us that we must know, we must do all we can to identify which are the best targets and figure out all the ways that we will need to work with the data so that we can make the right interpretation. And I think the report also did a good job in drawing attention to the challenge, the complexity of the planets and worlds that we will have to characterize, exo-Earth candidates, but even broader, just Earth-size and small exoplanets. So there were many people have worked on the decadal survey and input documents, and I'm really impressed by the effort and the quality of work people have put in. So thank to all of you who were part of the decadal in one way or the other. I will just point out, use this slide. I like this. And there's this is from the LUVOIR final report. There's a similar slide from the HABEX report. They decided to use their pyramids in the other direction, but both of these captures basically a thought process, a proposed process, if you like, on how these missions that were proposed as concepts for the Astro 2020, and the recommendation is somewhere intermediate between sizes of these two missions. How these missions or similar missions could go from basically looking for initially for planets around nearby stars, figuring out which are real planets. So these are the top steps on the top. First, use precursor information to establish a target list, then use multicolor point source photometry and proper motion to narrow down, constrain the orbit, search for atmospheric water. And once you found the atmospheric water and ensure that it's in the habitable zone, then you have what you may call a potentially habitable planet. And then you could go into in-depth characterizations through spectroscopy and further observations and revisits. This is a pyramid. I think it goes this way because you start with many potential candidates, but you narrow down to a few that will be particularly important. And those are the ones that you are going to spend most of your integration time. And indeed, getting this kind of data that is shown here is going to take a long time. I believe that this simulation assumed 2 weeks of integration, building up the spectrum in smaller wavelength ranges corresponding to coronagraph's efficiency. So this is an important process. And in this talk, I will explore how we can already help refine this process and inform the steps in this process. And I think this is extremely relevant, and it is basically where astrobiology really connects mostly to these missions. I will get to that. So as I mentioned, the HabEx mission has a very similar concept for narrowing down the planets. There are many exciting questions that can be derived from the decadal survey about what are exciting science goals for the next decade. And this is my list. And certainly this is not an exclusive list. These are the questions that, some of the questions that we are working on, and some of them I will address in this talk. And of course, many others are working in these questions too. I like the Astro 2020 as it is giving basically an intellectual framework for us to think about these problems. So one of the questions, and in this talk, I will not go into that, but I think one question that will be important is to further understand eta errors, the value of eta errors, and get further data to constrain that. That is important because it directly the yield of a mission in terms of times detected is directly proportional to that. So, but in this talk, I want to focus a little bit more on the diversity of planets and how we can push our understanding there, and how we can integrate information across different disciplines and data sets to improve our understanding. So some questions here: when is a planet really Earth-like? That means when can we really, for example, apply our climate models or carbon silicate cycle models? Through which pathways can truly Earth-like planets form? What processes can make Earth-sized habitable planets that otherwise would look potentially habitable inhabitable? Very importantly, I mentioned how valuable these targets will be in the missions. We have to, I think, try to do what we can to address the question which nearby planetary systems are the best targets for a search for biosignatures. How can we reconstruct likely planetary architectures from incomplete and uncertain data? I will get to this in the talk. And how many targets do we need for our science goals? Or in another way, as a function of sample size, what sort of questions we will be able to answer? And that basically directly leads us to what is the diagnostic power of an exoplanet survey or given a space mission architecture. What can we learn from 5 planets, 10 planets, 50 planets, or 100 planets? And related question, how important are ancillary data? For example, radio velocity surveys. So these are a couple of examples. There are many others that I think our community can work on and are working on. People are working on this and explore them further. I think one point that is maybe sometimes underappreciated is what is the diversity of potential Earth-sized planets. So we often use, for lack of better template, Earth as a template for what we may find. But the reality is that we know very little about Earth-sized planets and how they may differ. In the solar system, I think we have this beautiful example of Venus, which is almost an Earth twin in many of its fundamental parameters, yet its atmosphere, its surface properties, its evolution has differed greatly from Earth. They may have started in a similar part of the parameter space, but then they diverged through their evolution. So I think keeping that in mind, that very small sample in the solar system, and asking the question, what are the factors that impact whether or not a planet is habitable or not, I think it's very important. So there were many members of the community that pointed out this challenge, and so I led an ExoPag SEC study group, SEC 15, where we wrote a 100-page report on science questions related to habitable planets that could be answered. I led a white paper that I wanted to highlight here for the point it's making. So this white paper argues that there are many parameters and processes that are important to understand for a given planet to be able to say whether or not it's habitable or may impact habitability. And some of these are directly observable, right? We may be able to measure their size or radius, their orbit, depending on the method we are using. But some parameters and processes will be impossible to detect via remote sensing. or practically impossible. And so these parameters, however, and processes need to be constrained, and they cannot be constrained on a one-by-one basis on a single planet, but they can be potentially constrained by understanding the processes that shape these planets, including formation, evolution, and what we can learn from the demographics. So very similar arguments on the complexity have been made by Vicky, for example, Rory and others. I put there here this famous figure, the planets are complex, that really shows how many different processes can feed into impacting the habitability of a planet or a planetary system. The question that methodologically that I want to explore in this talk is how can we integrate information from different sources? So it is, I think, clear that the future of exoplanet exploration is not using one method and measuring all the properties of a planet at high precision. It is rather integrating knowledge from different planets, from different planet population, from different disciplines into a framework where we can use that to assess and interpret observations of single planets too, but in that statistical context. So that's where Alien Earth comes in. So Alien Earth is our NExSS program. And for those of you who are not so familiar with it, NExSS, the NASA NExSS for Exoplanet System Science, is part of NASA's ICAR Astrobiology Research Consortium. And it is supporting interdisciplinary research, and it's supporting it in a way to create research coordination network. Our Alien Earth program that I will speak about briefly is building on Earth in other solar systems, a previous team that a direct predecessor of Alien Earth, which we were funded between 2014 and we are in the final months. Earth in other solar systems, or EOS, our team was focusing on a question: how do habitables on Earth-sized planets and habitable planets form? So it was through 14 multidisciplinary projects, including cosmochemistry, astronomical observations, models, etc. And the team, I'm very proud that we have, I think our team has made significant contributions to the field. We have published over 150 refereed papers, over 5,000 citations. You may know many of the papers that came out. I listed here some of the high impact papers or particularly unique papers. You probably have seen some of these. Several of these have received hundreds of citations. What I wanted to point out simply that it is a large team. We have more than 40 people and 7 disciplines represented, contributing to many aspects and of understanding how do habitable planets form and how we can characterize them. In Alien Earth, which is our newly funded team, we started 6 months ago. It's an indirect continuation of EOS. It's not EOS 2, but it is building on EOS's results and strengths. It's addressing a different question. We are taking what we have learned from EOS and answering the question: which nearby planetary systems are likely to host habitable planets and life? In other words, putting together what the specific information we have about nearby planetary systems and the planets in them with a broad variety of contextual and statistical information to guide us in our assessment of selecting targets and then later supporting the interpretation of observations of targets or guiding follow-up observations. So again, this is a large team and I will not go through all the programmatic details here. I want to just recognize that you see many of my collaborators and team members listed in the lower right panel. It is an interdisciplinary team, amazing investigators. I really enjoy working with them and learn a lot from them. We have this team, international team with lead institution, University of Arizona. We organized this team into 14 projects, which are organized in 4 modules. I will just simply identify the 4 modules and explain how they are connected, but I will not go to the project level details. We start with module 1, which is exploring the conditions and timeline for planet formation. So this includes cosmochemistry, including sample analysis of Bennu, the near-Earth asteroid, and meteorites, meteoritic samples. But it also includes astrophysical simulations of forming planetary systems, as well as observational studies of protoplanetary disks and the planetary systems that are forming within them. That information is fed into module 2 in the form of advanced protoplanetary disk models. In module 2, we are exploring how the planet formation pathways are impacting planet composition. So if there are some major differences in how my planet forms, what will be the consequence of that in the final emerging composition of the planet? This then is fed in terms of predictions and modeling framework for planet compositions and planetary system architectures into an assessment of habitability and threats, including searches, specific observations of nearby planetary systems as we are searching for planets and planetary systems around them, to the assessment of dynamical stability of these systems, and also identifying potential formation pathways and just broad categorizations of their past and evolution for individual systems, so that we can potentially eliminate those that we don't think are likely to harbor habitable planets for various reasons. All of this is done, it is in addition to producing research results and new models and hopefully some breakthroughs. This is also encapsulated then into basically information that we use to guide next generation missions and mission design. So we have a project further improving constraints on ETA Earth, understanding how biosignatures can be disentangled or could be contaminated in transiting exoplanet situations, and also creating the kind of framework that I will be showing you on how we can assess diagnostic power, for example, of an exoplanet mission in terms of testing hypotheses about exoplanet evolution. So before going to the individual, and I decided not to give much more detail on the individual projects because that may be less exciting, but then transition over to highlighting a couple of research results that are all related in a particular way, that they are exploring how we can integrate information from different sources to actually guide future observations and to better interpret existing data. And this is just one of the ways to slice of the many results that we have from EOS and Alien Earth. Obviously, I'm only going to it doesn't even cover 10% of the studies we have done, but it will give you a flavor of at least some of the directions we are pursuing. And I'm quite excited about this result. So hopefully you will enjoy this too. So in terms of, as we move from towards characterizing planets in detail, individual planets in detail, and searching for life in the near future through atmospheric biosignatures, planets in the immediate vicinity of the solar system will be very important. These are the planets that are orbiting bright stars because they are close to us. And these are the planets that are also close to us. So when we are observing them and collecting photons from them, we start with an advantage compared to a planet that may be thousands of light years away. So it is worthwhile just to take a look at where we are in terms of establishing a census of nearby planetary systems. This is just a quick estimate here. Within 50 light years, which corresponds to 15 parsecs, it's very nearby. We have about 1,560 stars, and around those, we don't know the exact number, but we can estimate around 10,000 planets. And of those, there could be habitable on Earth-sized planets, maybe 500. Maybe some estimates would put it in a larger number, higher number. I would probably put it around 500. Question is, how many of those we know today? So we have about 166 exoplanets that we know out of the 10,000 probably. And of the habitable on Earth-sized planets, it's probably 5, maybe even fewer. So we are missing, in other words, more than 99% of the planetary systems and the planets in the immediate vicinity of the sun. These are, of course, the targets that, these are the systems that would be targets for example, direct imaging missions. So I think it is important that we try to recover these, identify them, prioritize them, prepare target selection. So what I already alluded to this, that our approach is to go beyond the observations that we can get from an individual planet, because that is so limited, and instead also complement that with statistical constraints on exoplanet population. So for this, it is important to consider what are the kind of trends that are emerging from the exoplanet population statistics. And this is a talk that I could not have given 8 years ago, because much of this is really new, but the result of, in large part, of the Kepler mission and the community's work on analyzing the population, exoplanet population that emerged from the Kepler mission. I will just show here, highlight a couple of the trends and correlations that we are using in the subsequent studies. This is not a complete list of neither of what we are using or what the community has identified, but it is meant to give you a flavor of the kind of information that is available now to us. So we have now a much better understanding, thanks to Kepler, of the short period planets. We have period distributions derived by multiple groups that for the occurrence rate of planets as a function of period. So we know that short period planets are very common, and they are, in this particular fit, they are represented well by a broken power law, for example. Many studies have focused on multi-planet systems and have identified that they share many similarities in their planetary architectures, including the orbital period distributions, and often they are found to be, the orbital period ratios are found to be clustered, for example, by Hay and Ford. So these give us statistical handle on where planets are more likely in a system, and if one planet is known, where the other planets may be. Many studies have already also found that planetary systems tend to be dynamically packed. So that means that if you add additional planets, oftentimes that will make the planetary system unstable. In other words, that is basically they are as close to fully packed as possible, at least in inner planetary systems. Planetary orbits are often aligned, so we have now pretty good handles on the inclination distribution. And importantly, it was also found, for example, by Weiss et al. And others, that planet sizes tend to be very similar. So this is the peas in a pod concept, where planets tend to cluster in sizes and tend to be similar. So these are some, there are also others, but these are some of the key correlations and trends that are well established by many groups have found, sometimes different parameterization, but ultimately matching the same data. So let me show you how we can use these and other correlations to better inform us about properties of planets. And so this basically, I picked Proxima Centauri B, which is both an exciting discovery, an exciting planet, and I think also an interesting starting point. And for us, some of these studies started there. So this was Proxima Centauri is, of course, the closest star to us. And in 2016, a study led by Anglada Escudé, a large international project combining many radial velocity measurements, used stellar wobble, high precision measurements to deduce and to discover the presence of a planet around Proxima Centauri. And while not all planets remain, some planets are not always confirmed, but Proxima Centauri, I think this is a very well established detection, and it was a really nice project. Very nice results. That was a demonstration, a tour de force, if you like, of what's possible. What I want to point out here is what we know about the planet, or rather what we don't know about the planet. The information we have is that it has a minimum mass, about 1.3 Earth masses, and then we know that it's very likely projected in, very likely orbiting in the habitable zone. But really we don't know too much about its nature. So it's often assumed in the literature that it is a 1.3 Earth masses rocky planet, but when we started out in 2017 and still today, we don't really know the composition of this planet or really the real genuine mass. That is because the radial velocity signal, so amplitude will depend on the planetary orbital inclination that remains unconstrained for Proxima. So we started a project with Alex Bixel, who was a first-year student in 2016, and we basically explored what we may be able to say if we supplement the information we have on Proxima Centauri, which is very limited, with statistical constraints. Could we predict what could be the mass distribution for the probability distribution for the planet? So because we have many M-dwarf planets detected by, for example, Kepler, it was possible to use at least an approximate trend of how likely planets are as a function of their radius. We could also use mass-radius relationships to translate this statistical distribution to a mass distribution. And there are differences and uncertainties in the mass-radius distributions, but it turns out that they don't fundamentally change the results here. So we used two different ones and explored others, but they don't have a major impact on the results. Basically, what comes from this is that if you have a size, a mass distribution, and it was already back then known that smaller planets are more likely to have higher density and larger planets are more likely to have lower density. So you could identify rocky and sub-Neptunes. And how we did it, we did it in a paper as a transition radius, which actually turned out to be a pretty good match to the Fulton gap that was discovered later. We also looked at 4 or 5 different parameterization of that. But if you combine these and then you basically consider what is the mass, the lower limit on the mass that comes from the actual observation, you can create a posterior mass distribution for Proxima, and which is shown here, and then also basic contributions from a rocky planet or more of a gas-rich mini Neptune planet. And so this shows that while the most likely composition is a rocky composition and the most likely radius is a small one, there is actually a long tail of this distribution. And of course, if the planetary orbit is closer to face on, Proxima's mass could be much larger. While this alone is not particularly surprising, this was the first example where we took statistical constraints with specific measurements, combined them, and made a statistical prediction for the nature of Proxima. I think what is relevant here is that the minimum mass people often use in, for example, modeling Proxima, where it's 1.3 Earth mass is assumed, is very unlikely to be the case. Proxima's expectation value is 1.6 Earth masses, almost independent of what assumptions you're making about this. So this was an example of combining this kind of information. We took that in the next studies to much further. And so I want to show you different approaches to the same general idea. So hidden worlds around nearby stars. I already mentioned that even though we have many planets and planet candidates that we know today, the vast majority of the planets in the solar neighborhood remain unexplored. We just don't know the planetary systems very well. Nevertheless, and I should point out that even when we detect we have 1 or 2 or 3 planets known in a system, in almost all cases, the majority of the planets in each system remains undetected. There are maybe a few exceptions to this, but it's generally true. So 3 years ago, we started on a challenge with my student, Jeremy Dietrich, to try to answer the question, if we had information about some of the planets in a system, could we predict where additional planets may exist? So this would be, of course, very exciting because it could guide future observations and help explore the planetary systems architecture. So the challenge here again is similar to the previous one, but it's more complex. We basically have system-specific data, so that is related to a specific planetary system. It is, however, incomplete and uncertain, and it will also be the same in the future. No matter how good missions we build, we will not really have very high precision measurements for most of the planet properties, and we often will not be able to detect all the planets in a system. So this is not just typical to today's state, but also to the future. And on the other hand, we have increasingly robust understanding of the exoplanet population statistics for short period planets. And that is going to continue to improve significantly. So it is important to combine these, which is what we did in Monte Carlo simulation. And equipped with this, we are able to make predictions about basically probability distributions for yet unexplored, undetected, undiscovered planets, what their planetary orbits, sizes, nature may be, and how many planets you may be able to add to the system. So this was the idea, and it was all implemented by Jeremy Dietrich, who has done an amazing work in a series of papers developing Dynamite, which is a dynamical multi-planet injection tester. It basically combines multiple trend level information, which is generally true to exoplanets, also not necessarily to each specific system, but as a general trend on planet radii, orbital period distribution, inclination distributions, relative size distributions, and we can create planets in a Monte Carlo fashion on orbits and then assess whether or not those systems would be stable. We use the variety of dynamical stability criteria. So this is just an example. This is a flowchart that shows the key steps here. And this has been now used in 5 papers with other papers coming up too. We start from input data, which can be a single system that we target, for example, Tau Ceti, or it could be all nearby planetary systems. We take the specific data to that system, which planets are known, what are their properties. And then we also use statistical models, just as I described, different distributions for the parameters. we also use dynamical stability criteria. So we have implemented different ways to assess whether or not the planetary system is at least short-term dynamically stable very efficiently. I will probably not go into details because of time pressure, but I will be happy to answer questions on this. But we have multiple methods and they actually provide extremely similar results, which is reassuring. We combine these in a Monte Carlo fashion. And with that, we are able to make predictions for where the next planets, where the most likely next planet in the system could be. So I will just show you a couple of examples, and I should mention that this is all available on GitHub. So if you want to run it on your favorite system, which some teams have done already, that's all available. But before I show you the results, I want to show you that this actually is working quite well. We have done quite a number of tests where we basically ran this assessment on different systems where we know planets and then we hit them from the algorithm. So for example, here you see Kepler 154 on the left-hand side. This shows the relative likelihood. So the higher the values are, and you see a blue distribution here, which are the Monte Carlo probability distribution, the higher it is, the more likely it is that if there would be one additional planet, it would be in the system. The green dots here show the confirmed known planets in the system. The only trick that we did here is that actually there are 2 more planets in the system, but we hid those from the algorithm. So Kepler, in fact, detected here multiple planets and we hid them. And so, sorry, we hid one here and one hid on the other system. And so what you see here, basically, as I clicked, this white cross was revealed. So our algorithm predicted that the period of the planet in the inner planetary system, if there is another one, it would be very close to 10 days. And in fact, just where the peak is, we found, this is where Kepler did detect a transiting planet, which was not fed to the algorithm. This is another system where we did a similar test. We hid this planet that is white crossed out, and our predictions were actually very close to the orbital period of the planet. And not only this works for the orbital periods, if you have a few planets in the system, also for the planet radius, this tends to work very well. So these are predicted and observed radii and inclination for this planet that we detected, for example, we predicted here, for example, and within 2 sigma, we match basically the inclination and the radius. So that's very encouraging. It does tell us that this is a typical planetary system, very similar to many other planetary systems in its properties. We did test this in the solar system too, inner solar system. So you see similar tests here. In the top, we used the Hill dynamical stability criteria. In the bottom, we used an N-body-based dynamical stability criteria. The results are extremely similar, so I will not go into details there. The key point is that, for example, if we, in the inner solar system, we hit Venus, or analysis predicted that there should be a planet pretty close to, but a little bit shorter period than Venus itself. And that basically is the most significant peak. If we hit Earth from the simulation, it did predict that there would be basically a planet almost perfectly on the same orbit as Earth. This is another planet radius prediction where we hit Earth, or you could hit Venus, and you would be finding basically that it predicts that these would be rocky planets in the inner planetary system. So that's quite exciting. It works for the solar system. This is another prediction where we hit Mars. This was a study led by the undergraduate student Ritwik Basan, who did an excellent work here. He also did, basically, in addition to these tests, he also did a temperature prediction. And for Mars, again, we basically can, within 2%, we can predict correctly the orbital period and also the temperature. It doesn't mean it will work for every system, but it does work for most systems that we were able to test this on. We then ran it on 54 test planetary systems. And so these are many TOIs. You may recognize some of your favorite. The red dots show known planets, and the blue shaded region shows where is the most likely that additional planets exist. We can order these because we can predict sizes and periods. We actually calculate the observability of these and identify which are the most promising targets to follow up. Since we published these, 3 of the planets have been also discovered here. So let me just show you one fun study. We focused we explored, for example, Tau Ceti among other nearby systems. This is always fun because some of these planetary systems, they are not only interesting for astronomy, they are also so much in the popular knowledge and related to the visions of humanity's future that they play important roles in science fiction movies and books, etc. So Tau Ceti is one of these. Of course, it's the closest broadly sun-like star, and there are many movies, including the Expanse, Star Trek, etc., that plays on the potential of habitable planets around Tau Ceti. But the question is it likely that there are probably habitable planets? So Tau Ceti is basically a nearby star. I will just see if let me just skip this and okay. This is just a view of the Tau Ceti system as we predicted. What is known about Tau Ceti is that it has 4 known planets from radio velocities detections and 3 candidates. And further out, there is a debris disk that was dissolved by ALMA. And much further out, there may be a potential Jovian planet. Our analysis, basically, if we didn't tell the analysis package dynamite about the planet candidates, it actually predicted peaks, highest likelihoods, matching B, C, and D. These are 3 planet candidates. So actually, our analysis predicts, even without the knowledge of those signals, that it is likely that there are planets there. And in fact, there are 3 radio velocity peaks there. And we also predict that with higher likelihood that there would be 1 more planet in the habitable zone of Tau Ceti. Size-wise, these are larger than Earth-sized. So it is a good chance that this predicted exoplanet 4 is also larger than Earth. Nevertheless, this is a system that is, of course, very important for future studies and direct imaging, for example, too. So we have, I will skip this. This is another system, the closest multi-planet system with 6 known or probable planets, and also with the closest transiting planets. And we, again, basically were finding additional support for planet candidates in the system. And we predict that there is a planet that is very likely inside the habitable zone. At the same time, this paper also led by Jeremy Dietrich in collaboration with Renu Malhotra, it also provides advanced orbital stability analysis and new features. I will skip this paper too. I will just end with basically this has now been applied, this approach, to a very large number of planetary systems, and the number is growing. Teams other than us have already also applied this. So this is a study led by Kevin Hardegree-Ullman, where in another Kepler system, predictions were made correctly. So there is a lot of support that this statistical approach is working quite well. There are also other teams that started to look into making similar predictions based on a different methodology, but same concept. So I have more slides than I will be able to cover, so I will not do that, but I will just mention the types of results that we could also reach with this kind of approach, where we take statistical information to make predictions about properties of planetary systems. We, in a study led by Alex Bixel, we have addressed this long-standing problem that a direct imaging mission from a single epoch will not be able to distinguish between planets at inclined orbits, long periods, phase angles, small and large planets, and high and low albedos. There is a significant degeneracy. This detected dot is consistent basically with many of these large and small planets and different orbits. We showed that taking and making use of the information, statistical information that is available on exoplanet demographics, we can very significantly accelerate the follow-up of these false of the correct ExoEarth candidates and sort out the false positives that otherwise dominate the sample. So this can result in a factor of several enhancement in the efficiency, but even under conservative conditions, it's at least a 33% enhancement and better use of these missions and the telescope time. And let me skip the last slide, and I will just go to the summary here and then open up for questions. I don't want to take too much of your time, but as a summary, let me just reiterate that thousands of exoplanets have been detected, but we will need to find for our next steps planets that are very nearby and understand those planetary systems, because we'll always have incomplete and uncertain information about most planets and planetary systems. It is important to incorporate statistical understanding of the exoplanet population, what we can learn from planet formation, planetary evolution, and biology to inform basically our interpretation of the known planetary systems, what we know about them, and interpretation of future observations. In the frame of Alien Earth and EOS, we have been developing such an integrative framework. And I showed you some examples. I had many more that I could not cover now, but in many ways, we can directly link these to guiding exoplanet missions, prioritizing targets, and looking into the hypotheses that these missions can test. We can assess the value of radio velocity surveys, for example, supporting observations, etc. And so I will just leave you with this general idea that with Alien Earth, we are pursuing this direction. I'm very happy to hear about your research that may connect to it. And everything we develop within Alien Earth is done in a modular way, in a way that connects to the community, the NExSS community and beyond. And we are very happy to collaborate with you and your research groups. Let me stop there, and thank you very much for your attention.
All right, great. Thank you very much, Daniel, for a fantastic talk. We do have time for questions. So as I mentioned at the beginning of the hour, if you have a question, you can raise your virtual hand and I'll call on you. And if you are able to, please turn on your camera and ask your question to Daniel directly. Otherwise, feel free to type it into the chat and I can at least ask it. So does anybody have any questions for Daniel? All right, well, I'll ask one then, since my camera is on. So the dynamite framework, I assume that there must be some degradation in the predictive power as you go to larger semi-major axis and larger stars, just because we have, I assume most of it is based off of the short period planets. So about where does that, is that true? And is there sort of a fall off? Like where does that really?
Yeah, that's a very good point. And so I should maybe stress, if it's needed, that so basically the assumption here is that the predictions are most likely to be correct if your planetary system is typical to the Kepler population, which is, we think, is fairly typical to exoplanetary systems in general. There are systems that are exceptional, and for those systems, these predictions would likely not be fully valid. So one of the ways where the Kepler sample becomes incomplete is if you go to long periods, and that is basically just because of the final duration of the Kepler mission. Another way it is that if you go to a spectral type, host spectral type, that is atypical to the Kepler population. And so in those cases, our predictions will have less reliability. We did the tests though, for example, for Mars, because it is a fairly long period planet compared to the exoplanet population within the Kepler, and we were interested whether or not that works. And in that case, it did work very well, so we did get it within 2%, but it's generally true that the outmost planet is less well constrained than planets in between two known planets. And we will need to expand on the data, I think, if we are to broaden the spectral type range to which we apply the systems. But right now, basically, based on tests and Kepler data and RV data, it seems to be working quite well for shorter period planets, so basically maybe 200 days or so, and for even early M dwarfs and sun-like stars and K dwarfs.
Okay, yeah, great, thanks. Let's see, we have a question in the chat, which I think is just mainly a clarification about if Tau Ceti is a nearby system, I think. Does Tau Ceti have nearby planets is the actual question.
So yeah, I kind of went through a little bit quickly, but basically, so yes, so Tau Ceti is the closest sun-like star, single sun-like star. And it had basically from radio velocity studies, it had planets and planet candidates, and our analysis supports the plant candidate's genuine nature, and also predict that it's very likely there's at least one more planet in the habitable zone. But our prediction is that it is probably larger, maybe significantly larger than Earth. It may be more of a mini Neptune. It is a prediction. We also can predict and do predict amplitudes, for example, and observability of these systems. So the nice thing about predictions is that they can be tested. And TauSat is a system that is being monitored for further planets through radio velocity, and it will be one of the top targets also for direct imaging.
Okay, great, thank you. And before I read the next question, I want to say if you have typed something in and you do want to ask it to Daniel directly, maybe you can raise your hand, and then you can. I'll know that you do want, in fact, ask him directly. But the next question is from Taylor Walton, who asks, how do you expect the new proposed LUVOIR telescope to help to develop the dynamite algorithm?
Yeah, so I think that it's a very good question. So basically, when we developed this algorithm, the synergy with future missions and future observations was, of course, at the very heart of this effort. On one hand, these I think that there's a lot going in both directions. With our algorithm and this kind of predictive assessment, you will be able to guide target selection for missions. And then when you execute those observations, you can then test basically the predictions and so further improve your models if needed. I think by the time we will fly something like LUVOIR or some similar version, we probably have figured out most of the things about this predictive analysis. Where I do expect very significant new data to come in would be from the Raman Space Telescope. It is going to use micro lensing, and it will be sensitive to exactly the kind of planets Kepler was not sampling very well. Intermediate periods or longer period planets that 3 to 8 AU or so separations. And that population is not well sampled. So when we add that information, I think that is really going to make this algorithm much more powerful and applicable to long period planets.
All right, great. Thank you. And I think the next question is from Tim Livengood, who will ask it directly.
Yeah, I thought dynamite looks really cool. I'm curious though, at the current stage, if you were to leave out from our solar system 2 consecutive planets like Earth and Venus or Earth and Mars, would you recover them as one super planet, or would it actually be capable of recovering them as two planet candidates?
Very good question. So I don't think that we did exactly that, but we did a very similar test for Kepler planets, and they are part of the first papers that we published. In Kepler multi-planet systems, where you have 5 or 6 planets, we left out 2 planets, both consecutive and non-consecutive planets. And the answer is that depending on the spacing of the planets, in most cases, we actually can figure out that there will be 2 planets there. There are a few cases, if the spacing is such, maybe you could explain it with 1 planet, but because of the dynamically packed nature of most of these planets, and because of the similarity of planet sizes, it is very unlikely that you have in between 2 small planets, you would have a giant planet that would provide enough dynamical influence to make that planetary system packed. So we have, if you speak about leaving 3 planets out, then you start to end up with much less reliable results. But in most cases, when we tested for the 2 planets, you can figure out that there are 2 planets, not 1.
All right, great. Thank you very much. Well, it looks like that's the end of the questions, and it's just about 4 o'clock here on the West Coast. So why don't we wrap this up? And please join me in giving Daniel a round of applause however you can, whether turn on your camera and mic or giving him some emojis. So thanks again, Daniel, for a great talk.
Thank you, Rory, and thanks for everyone for joining.
All right, take care, everyone. Have a great holiday, and hopefully we'll see you next week.